With the above lesson in mind involving the importance of data visualization, along with the broader perspective on the class of problems we are trying to solve, we now create a new subclass of my functions that starts to put all the useful attributes of a root finding problem together based on the bisection algorithm. First, we need to take stock of the data and method attributes we are collecting inside of this class. Now, for data attributes, the obvious data attributes for this class are the function f, the a and b parameters defining the interval where we look for a root, and n being the number of maximum iterations we might take for the algorithm. However, we may not know what the a, b, and n values should be for a particular f when we are first considering the function that we want to find a root for, because maybe we haven't plotted that function yet, and we don't really know where we're searching for where a root should be. So that's a good argument for defaulting these values to none types upon initialization. And then that means we should have a method attribute that can set these values similar to what we did for the root parameter, where we had the method set_root in the myFunctions class from above. Now, the root computed by the bisection algorithm is obviously another data attribute, but it shouldn't be determined at initialization. It should be determined and set when the bisection algorithm actually executes. The tolerance parameters for the bisection algorithm are other data attributes, but these really seem like the types of attributes that should have some default values based on, let's say, typical use cases from prior experience. In other words, we default to values that feel right. Method attributes that we should consider: the compute bisection algorithm, of course, and then the method I was just mentioning for setting the a, b, and n parameters, as well as those tolerance parameters to other values we determine are, let's say, better than what was assigned, if anything, upon initialization. Such values may be determined by examining a plot using the inherited plotting method associated with the myFunctions parent class. As a suggested activity below, you should add docstrings and code comments to the class and the various methods as you see fit. I have some in here. I don't have that many code comments. You might want to add a whole bunch more, and maybe you even want to add doc test and figure out how to run doc test with a class. I haven't shown how to do that yet. That's coming up. But if we look in myFunctions enhanced, it's subclassed from myFunctions. This is an enhancement of that class in my perspective. So it's like a child, but it's growing beyond its parent. And so it's going to have that root, which is probably none, that of a none type, and it's using that super command to basically initialize the parent class. Excuse me. We see that we have a, b, and n as none types. We have these default tolerances, and the first thing we do, and I'm using this all command here, so if all of these things are present, meaning that none of them are none. So you can check what this all is doing, this all command. All, and if you give it things that are not none, this should be returning a true. In fact, I'll just go ahead and show you a code cell right above. So if I have all, and let's say I give, let's say 1 and 2. Let's say I just run that. Oh, excuse me. It takes exactly 1 hour. It takes a tuple. Let me take, like, I think that's what I was doing here. Let me just, there we go. There, all that's like, that's an argument. It's like 1 and 2, so that's true. Now, what if I have 1 and none? That's false. So not all of these are none. This is really useful for the initialization. I think I have this working here with these being individual ones, individual values, but perhaps I should just put it in a tuple when I look at the all command. Let me hold it. It does say it has an iterable. Okay, so I need to put this all in an iterable. So I'm going to put a, the tolerance there we go. Put it all inside of an iterable, which is like a tuple is an iterable object. So if everything is available upon initialization, I'm going to go ahead and call the compute bisection method that is now a method attribute within here. You see I have a set bisection parameter, and they're all defaulted to none, which means you can individually set these at any time, and it will check to see if any, when you're calling it, if any of the ones that you're setting are not none, it will just set that data attribute to whatever value you wanted it to be when you call this method. When you call the compute bisection, you should just compare this code to the compute bisection algorithm you saw above. The big difference is I'm using self.a instead of a and self.b instead of b because I have to use the data attributes of the object. I also have something where I'm checking if a, b, or n is none. then I want to raise an attribute error right away. So just some basic, thoughtful engineering aspects into the software. So there we go. Let's go ahead and run that. Oh, and the output, instead of returning things from the algorithm, before I had a compute bisection function and I wanted to return A, B, and C, I'm now also keeping track of the iteration like A, N. And so I have self.A and self.B. They actually never change. What I'm doing is I'm storing AN, like the final interval, AN and BN. These get created as new data attributes, self.AN, self.BN, so I can actually see I can compare the final interval to the first interval, because maybe I want to do that. And then I set whatever that C value is at the end. I use the setRoot method, which was inherited, again, from the myFunctions parent class. I now set it there. And notice I don't have any plotting. I like this. The whole point of this class is kind of nice in how I organize my code. This is really all around enhancing the function to allow it to be interrogated with a bisection algorithm while also inheriting all the plotting features and annotations that we had from before. So this is, again, a usefulness of using classes and subclasses to help organize your code. So let me go ahead and run that. I think I might have already done, but I'll go ahead and run it. I'll just take out these extra lines that are superfluous. There we go. And now let's explore how easy it is to use this class to study a function and approximate its root. Let's go back to this third order polynomial. I'm just going to say this is f new, and here's a fancier new version using my enhanced function class where I pass this new to it. I could also just put that lambda function right there directly in this, but I'm just showing it different ways. Now, so I create that function, and here are steps that you could use now to interrogate the function visually, use the bisection algorithm and to estimate a root, and then plot and annotate your root with just a few lines of code in terms of calling these methods within the object that you've instantiated. So first, you might create your object. You now plot the function. You say, oh, there's my third order polynomial. That's great. I have my third order polynomial. I see that there's a root in here between -1 and 3. And if you just were to call compute bisection, this will raise an attribute error. Why? Because A, B, and or N are not set. This is exactly what I told it to raise because I never set A, B, or N. And I have to go, oh yeah, set my bisection parameters. Let's say A is -1, B is 3, and N is 10. And now compute the bisection. And now when I compute the bisection, remember that final interval is computed, that root is set, and because that root is set, and I can say, well, now plot it and show the root, it not only is it plot, but the annotation is automatically made as well. So there you go. Once you have all this stuff kind of organized in your code, you could take any function you want. You could create new instantiations of this object, and then you could just repeat these steps. You could say, I'm going to plot it over different ranges of values until I find one where it seems to cross the x-axis. And as soon as you find it, you could set your bisection parameters to be the points where it was positive and negative on either at 2 points where it has different signs, or it's positive and negative, and how many times, up to how many times you want to try to do the bisection algorithm to estimate the root. Then you compute the bisection, and then you're good to go. You have the root approximation, you can do the plot, and you can show the user or yourself, here's approximately where the root is. So this is almost to the end of this Part A lecture notebook as far as root finding is concerned. We do have some more stuff involving numerical integration. There is an activity here which I will put the solution to, or I'll discuss the solution in the next part of this video. And there's 2 summary activities here. I want you to have an activity summarizing what you found for root finding after you go through this first activity here. And then that will conclude the root finding part of this lecture notebook, and then we'll do numerical integration. But up next, we'll talk about this first activity. For this activity, you are to play with the bisection algorithm. Now, there's a few notes I have here. You may want or need to create many additional code and markdown cells as you work your way through this activity. The second note, you will probably need to explore some plots of the function first. For example, by experimenting with the plot attribute of instantiations of the myFunctions enhanced class to determine viable candidates for the values of A and B in order to capture the root for the functions you are playing with. Suppose the root is 100, for instance. Then you need to set up the problem and any associated plots around this value to get things to work properly. Note 3. It is okay to show examples that produce errors. This is in fact encouraged as long as you explain the errors. But you should also show results that do not produce errors. So in this activity, you should do the following. And by the way, some always means at least 2. At least. Create instantiations of the myFunctions enhanced class for some, meaning at least 2, lambda functions of your choosing that have roots. Or if you want things to have errors, you could do stuff that don't have roots. Just explain your errors. These must be different. So I am saying at least 2 that have roots. So you could have some others that don't have roots, but at least 2 of these have to have roots. These must be different in non-trivial ways from the functions we have already explored in this notebook. A trivial modification would be to copy and paste a function previously seen above in this notebook and change it in some minor way, like changing a coefficient or just changing the power of some term in a polynomial that I already provided. Do not do that. Be creative. Look at new, different types of functions that you can code up and explore the roots. Illustrate the annotated approximations of these roots for each lambda function using the inherited plot method attribute of the associated instantiation of the myFunctions enhanced class. Summarize and interpret results in the markdown cell you create below the plots. So I have a markdown cell here. You could just put it in there. You might have more that you want to put in. That's it. Basically what I'm asking you to do is go through these steps I just showed you above. But you do stuff with new functions. Just explore more complicated functions. Just different things. Hopefully make it kind of interesting for yourself. And then you go through this process where you plot, you then use your plot information or your various plots to then find what you should set the bisection parameters to be, compute bisection, show the root. Do that for at least 2 functions that have roots. Perhaps do some that don't. And just explain your results. Interpret it. So if you had that picture, that figure, how would you summarize and interpret what you're seeing to somebody else? So you show that figure, and then what words would you put around it? What would you see? Could you interrogate? Here's something that's interesting for you to consider. These data attributes, self.an, self.bn, you could look at what these values were, and you could compare the final interval to the initial interval and just see how well it worked in terms of, or just explain what that means in terms of the relationship to the root C that was ultimately found, and just a comparison of how many iterations it must have taken to get to AN and BN compared to A and B. You want to know how to compare like how many iterations it must have taken, because I'm not storing the current iteration number inside of anything. Just compare the length of it to the original length. And as a ratio, it should be some factor of 2 raised to a power. That's what it should be. It should be a fraction. It could be like a half, a fourth, an eighth, so on. And that would give you a sense of how many iterations were taken. So think about how you would explain and interpret these results with what you have to work with. So that's kind of it. Like, I've already kind of shown what you need to do to this activity in terms of these steps above. So I don't want to put more things down where I'm just taking functions off the table that you can't use because I'm using them, and I want you to use different functions than what I'm using. But that's what I want you to do. I just want you to go through this process of how you can use classes and these objects to do something like solve a root finding problem, do some visual storytelling, and explain the results. That's it. That's all I'm asking you to do in this activity. And then I want you to just do your summary for this part of the notebook down below. Thanks for listening.